In this lesson, we're looking at the trigonometric functions of compound angles. Now, a compound angle is just an angle that's made up of two parts, so it might be two parts that are added together or perhaps subtracted. Now, before we get into it, let's just look at a little bit of revision. Now, perhaps you won't need to write this down if you think, yes, I know that, but perhaps it is a good idea to write it down again. We've already looked at this before, so I'm saying let's recall that if we have a circle here, and it's a circle with a radius r, so I've labelled these points r and negative r, so I can also label this as radius r. And I've got a movable point here, I'm just calling it xy for now, and saying that it could move around and sit anywhere on this circle. Of course, the centre of the circle is the origin. Then what I can do is label an angle here, which of course would have to be an angle between 0 and 360 degrees, or 2 pi if you're working in radians. Because as this point moves around, the size of this angle is going to change, isn't it? It's going to move through the first quadrant here, the second and the third and the fourth, and get anything up to 360 degrees in size. Now, I could drop a line down, straight down from that point, and it's going to meet the x-axis at a right angle, isn't it? Now, can we tell if this is the point xy, the length of this? Of course we can, it's going to be x. And the height of this triangle is going to be y. So now if we look at the relationships in that triangle, we can see that the sine of theta is just opposite over hypotenuse. So if we want to rearrange that so that it's in terms of y, we could say that y is r multiplied by sine theta, okay? Similarly, cos of theta is going to be adjacent over hypotenuse. So to get the x on its own here, we could say that x is r multiplied by cos of theta. So using this and this, we can say that we could call any point on the circle xy, but we could also name it something else. We could call it r cos theta, r sine theta, because those are its x and its y coordinates. Okay, now we've got a new circle, and it still has a radius of r, and it still has its centre at the origin, but this time I've put 2 points on it. I've called them A and B, and I've made those points by making a ray, which is passing all the way through here, and this ray beta passes through my circle at B, and this ray alpha passes through my circle at A. Now, remember that we measure angles as rays, always starting from over here. So this angle that's just in here would be beta, and the angle that goes from here all the way around to that ray would be alpha. So actually we can label this little angle in here as alpha minus beta. Now, why would we want to do that? Well, we're generating a proof for the first one of our compound angles, and this one is going to have 2 parts that are actually subtracted. So now let's come up with a nice simple expression for A and for B in terms of R and alpha and beta. We've already just seen how to do that. If we're looking at this point A, we can see that the angle that we're dealing with, the theta in other words, is actually going to be alpha. So it's not R cos theta, it's R cos alpha, because that's the angle that we're dealing with to get around to that ray. And we have r sine theta as its y value. And similarly, B is the point r cos beta, r sine beta. Okay. Now, we want to look at the distance AB, because if we can come up with 2 different ways of finding that distance in terms of all these r's and betas and alphas, then we can equate those two and come up with an expression that will help us find it every time. All right, so let's think of what methods that we have for finding this length AB. Well, firstly, I'm thinking it's sitting in a triangle, isn't it? And we already know a few things about this triangle. We know this angle here, and we know this side is r, radius, and this side is also r. So if we wanted to find that side there, we could use the cosine rule, couldn't we? All right, let's have a look at that. So use the cosine rule. To find, let's find not just AB, but AB squared, okay? Because the cosine rule says AB squared is equal to one side squared plus the other side that you know squared minus 2 lots of this side times this side, cos of the angle that's opposite the side we're trying to find. So we want cos of alpha minus beta. And now tidying that up, we can see that we've got 2 r squareds there. And in fact, we can see that now we've got 2 terms this one, and they've both got 2r squared in them. So really we could make it simpler by factorising and saying we have got this. Okay, now what are we going to do with that? Well, at the moment, not much. We don't know what r is, and we don't know what alpha and beta are. So we've got here a recipe for finding ab squared. But what we want to find it for is we want to find 2 different recipes so that we can equate the 2 together. Okay, so we need now another method, not the cosine rule. How else could we find a formula for this length AB? We could use distance formula, couldn't we? So using the distance formula, and that's just the basic formula that's really just Pythagoras. It's just looking at how far it is from here to here. Now, if we asked Pythagoras what to do, we would get this. We'd get a little right-angled triangle in there, wouldn't we? And we'd say that this side, AB squared, is equal to this side squared plus this side squared. And that's really all the distance formula is. It's Pythagoras in disguise. So we would say that AB squared is equal to this side squared. Now, how would you work out that length? Wouldn't you say it's this height, or the y value of A, minus the y value of B? In other words, it would be this minus this, r sine alpha minus r sine beta, all squared, plus, how do we square this side? Well, we need to find out how big the side is first, and we need to do 1x value, cos alpha minus r cos beta, and we'd need to square that. Okay, now if I expand that out, let me just move you across a little bit, I'm going to get a lot of terms. There's a couple of ways you could do this. You could pluck the r out of each part here and square that separately, or you could just leave it in. It's much of a muchness either way. I might just leave it in this time. So expanding this, I get the first term squared. I get this term multiplied by this term doubled as my middle term, so I've got minus 2 r squared sine alpha sine beta. And then I get this last term squared, and it was a negative, but when I square it, it'll be positive. That will be r squared sine squared beta. Don't forget that when we write sine squared beta, that's the same thing as sine of beta, all squared. And you could write it that way if you want to. This is just the notation that we tend to use. Okay, now I've got to add the 3 terms that I get when I expand this out. I'm going to have r squared cos squared alpha minus 2 r squared cos alpha cos beta. Can you still see that? I think so. Sorry, it's a bit small. Plus r squared cos squared beta. Now, there's a lot going on there, but let's have a look at how we can simplify it. Every single term has got r squared in it, so let's start by bringing that out the front. Okay, what else do we know? We've got sine squared alpha. Let's just tidy this up. And we've got plus cos squared alpha. Now, let's think of that identity that we already know. We know that sine squared anything plus cos squared the same thing equals 1. So that means I can take this one and add them together and get 1. So let's write this down. I've got the 1 from those 2. And let's maybe circle terms when we've used them. Okay, looking for something similar, here I've got sine squared beta plus cos squared beta. And of course, just with the r squared, which I've already brought out the front. So that gives me another 1. And then these terms here are not like terms. We've brought the r squared out, but we can see that we've got 2 sine alpha sine beta, and we've got minus 2 cos alpha cos beta. Okay, now tidying up here, 1 plus 1 is 2. So instead of writing it all out again, I'm going to be a bit cheeky and just pop that in there. Now, I've got 3 terms here. They've all got a 2 in them. So I'm thinking next step is probably to factorise a little bit better and bring my 2 out the front. So now all I've got is 1 minus, whoops, not a 2, silly me, 1 minus sine alpha sine beta minus cos alpha cos beta. All right, can you see what I'm going to do with this now? Well, we can see that AB squared is equal to this. It's 2r squared multiplied by some stuff in brackets, but it's also equal to this 2r squared multiplied by some stuff in brackets. So the brackety stuff, they must equal each other. Okay, so let's write that out. Therefore, we can see that 1 minus cos of alpha minus beta is equal to 1 minus sine alpha sine beta minus cos alpha cos beta. Okay, now let's tidy this up a little bit more, but be careful that you don't just say, hey, they've both got 1 minus some stuff. We can't just get rid of the 1 and the minus and say that this is equal to this. We need to be a little bit careful with our signs. It would be smarter to say, let's subtract 1 from both sides. We could definitely get rid of that. But if we want to get rid of this awkward negative that's out the front here, then effectively we need to multiply or divide both sides by -1. And that's going to change this side into the cos of alpha minus beta. But multiplying both of these terms by -1 is going to make them both positive. So we find that it's equal to sine of alpha sine of beta plus cos of alpha cos of beta. Okay, now that is our first identity that we've found, which is a trigonometric function of a compound angle. Now it's a compound angle because it's an angle where we've got two parts here, one minus the other, and we've got a little recipe for how to find it. Now we've already seen that y equals cos x is an even function. That means if you take the cos of a negative angle, you get the same answer as the cos of the positive counterpart of that same angle. So whether we've done alpha minus beta or beta minus alpha, really no matter what size these angles are, anywhere around our circle, we're going to get the exact same result.